This video proposes forensic methodologies for evaluating excessive loss of contact in racewalking events. Racewalk judging is always subjective and often controversial. Thus, having photographic evidence helps to remove subjectivity. Ideally, record the video with the camera on a tripod in a set position. Further, the video should not be shot panning the camera as athletes progress, because a moving background makes it difficult to measure accurately. Racewalking, as defined by the World Athletics Rule 54.2, states that racewalking is a progression of steps, so taken that the athlete makes contact with the ground, so that no visible, to the human eye, loss of contact occurs. And the advancing leg must be straightened, i.e. not bent at the knee, from the moment of first contact with the ground until the vertical upright position. This definition is highly subjective, as there's no objective measure as to what loss of contact to the human eye means. Evaluating loss of contact to the human eye. These methodologies only look at the loss of contact component, which has been studied as recently as 2019. Hanley states that 40 to 45 milliseconds is an appropriate threshold to adopt as visible loss of contact. This range is one accepted by many officials and a reasonable metric. We are also proposing to add 2 more metrics to the evaluation. Our studies indicate that more than 14 to 15 centimeters of flight distance per step across a stride and a summation height loss of contact through a stride of 100 centimeters or more, when measured with a 120 frame per second camera, correlate to a visible loss of contact. However, before we begin, we need to calculate the number of pixels per centimeter in each video clip. Photographs do not have a built-in scale or legend, so we have to use ingenuity to determine the number of pixels per centimeter for each photograph. Identify the 2 frames of the stride with the leg in the vertical position, and measure the number of pixels from the sole of the foot on the vertical leg through the top of the athlete's head. Compute the average measurement, because there is a varying angle and distance between the athlete and the camera. Next, look up the athlete's height in centimeters, most commonly found on the World Athletics or Wikipedia websites. Based on this information, divide the total number of pixels in our computed average by the height in centimeters to get the number of pixels per centimeter in the images used for this athlete's analysis. Loss of contact time is the number of milliseconds an athlete has both feet off the ground simultaneously. While this can be measured precisely in a lab setting, the accuracy of measurement in a race setting is dependent on the frame rate of the camera used. The higher the frame rate, the more accurate the measurement. When evaluating racewalking, we have found 120 frames per second to 240 frames per second to be ideal. Obviously, 240 frames per second would appear more accurate. However, often the higher frame rate comes with a lower resolution, so a balance must be struck. It's important to note that observable loss of contact time is not equal for every step. Due to the camera angles or asymmetry in the stride, there is frequently visible and measurable differences in loss of contact time per step. Therefore, we measure the loss of contact time for both steps in a stride, and then we compute the loss of contact time as both a worst-case step and also an average. To perform the actual measurement for each step, we need to determine the time interval of each frame of the camera. For example, if the camera was recording at 120 frames per second, for each complete frame of loss of contact, we add 8.3 milliseconds to the flight time. A complete frame of loss of contact is when both feet are off the ground in the previous and next frames. For the first frame with loss of contact, we make a subjective call whether the transition to the flight phase is immediately before, somewhat before, or significantly before the frame. When it's obvious that the athlete is off the ground for a significant portion of time before contact is made, we add a subjective amount of time, usually equal to 1/3 or 2/3 of the time for each frame. We perform similar calculations for the last frame of loss of contact. For example, observe how we calculate loss of contact in milliseconds for the following athlete. The first image shows the rear foot in contact with the ground, so at this moment there is no flight phase, and our total count of flight time is 0 milliseconds. The second image shows the rear foot just after it loses contact with the ground, as well as the front foot being off the ground. We need to look at the next image as well and estimate what portion of a full frame the athlete is off the ground. In this case, we subjectively state the athlete is off the ground for 1/3 of a frame, or 2.3 milliseconds. Therefore, we add 2.3 milliseconds to the total time, and now we have an accumulated time of 2.3 milliseconds loss of contact. The third image continues to show the rear and front feet off the ground. Since the previous frame also had both feet off the ground, we add an objective 8.3 milliseconds to the total flight time, and now have an accumulated time of 10.6 milliseconds loss of contact. The fourth image continues to show the rear and front feet off the ground. Since the previous frame also had both feet off the ground, we add an objective 8.3 milliseconds to the total flight time, and now have an accumulated time of 18.9 milliseconds loss of contact. The fifth image shows the athlete with a lead foot in contact with the ground. We compare the previous frame to this one, and add a subjective amount of time based on how much of the frame we subjectively believe the athlete is still in flight between the frames. In this case, we believe the athlete to be off the ground about 1/3 of a frame, so we add 2.3 milliseconds and get a final loss of contact time of 21.2 milliseconds. Flight distance. Flight distance is achieved by measuring the length traveled from the moment the rear foot leaves the ground until the moment before the front foot strikes the ground for each step in a stride. Here's an example using a 120 frame per second camera. We place two images in a single Photoshop file. The first and last frame the athlete is in flight. We draw a vertical line from the rear of the foot in both layers, and then measure the distance from one line to the other in pixels. We already know the number of pixels per centimeter. Therefore, we can calculate the number of centimeters in the flight phase. We repeat the process for the second step. Let's now compute the summation height loss of contact through a stride. It is necessary to determine where the ground is in relation to the athlete, and then measure the height of the front of the heel to the ground, and add it to the height measurement for the rear toe above the ground. Load in Photoshop the image with the rear toe about to leave the ground. Mark where the rear foot is in contact with the ground. Continue by loading the next image in the sequence, where the forward heel has just made contact with the ground. Draw a line from the original point through the forward heel strike. Check that the line is positioned properly for both points of contact. Next, the image just after toe off is loaded, and a measurement from the heel to the ground line is recorded and combined with a measurement from the ground to the toe of the rear foot. This is repeated for all frames. We compute the worst summation height loss of contact for one step, as well as the average for a stride. Not shown, this process is repeated for the other step in the stride. We have shown how to calculate visible loss of contact employing three metrics: flight time, flight distance, and the summation of height loss of contact. Accumulated data from these metrics for a racewalk event should be compared to the judging history of the event. Judging evaluation would correlate the loss of contact yellow and red paddles shown on the race summary sheet to the photographic data. Then, controlling for race conditions and judging positions on the course, this enables us to more accurately evaluate the judges.